Today's speaker is Professor Evelyn Hu, the Tarcoin Professor of Applied Physics and EE here at Harvard. And her group does really pioneering work in the creation of deterministic color centers in photonic crystal structures, right? Predominantly for making qubits, for making memories for optical networking and the like, and she'll walk through that space. But I also hope that she'll tell us a little bit about some of the idiosyncrasies associated with creating color centers. The fact that with color centers, you're kind of trying to make lemons into lemonade, right? And it's not always obvious what the recipe should be. So
Thank you so much, Bill. And thank you, everyone, for coming here. So in answer to Bill's question, it's all idiosyncrasy, but that's the fun part. I'm delighted to be part of the CNS seminar that talks about quantum. And in thinking about the topics that I could talk to you about, this topic that I'm going to talk to you about, which is a representation of what my group does, strongly depends on all the resources in the CNS to create the means for understanding what we're doing. And it's also a technique that's been newly generated principally by Aaron, who's sitting in the back, and Jonathan. There are other people in my group who've been involved, but these are the people who've spearheaded this effort to design a new kind of technique to paint defects, qubits, hopefully where we want it, in a way that we get immediate feedback about what we're doing. So from those points of view, the building blocks that I'm going to show you heavily depend on using the techniques and resources from CNS, but also we think that we've added a new kind of instrumentation to do fabrication, and that's what CNS is all about. So I'm going to be talking about creating color centers, and as Bill has hinted, these are interesting from the quantum point of view. And why? So many people are searching for the follow-on to the bit, the unit of information that has dominated our life, probably since this is the first transistor demonstrated in 1948, but really the proliferation has happened probably since the 1960s. So what, 60 years? We're still dominated by the information that transistors can provide for us, often digitally, not always digitally, and that's in all your laptops and smartphones that generate communications, computation, and networking. So in the successor to this bit, we think is going to be a quantum mechanical bit or a qubit, with important new properties that make it, we hope, much more efficient in representing information and transmitting information across long distances. And right now, if you've been paying attention, this is an exciting time because companies like Microsoft, like Google, like AWS, major companies, IBM, have invested a lot of resources into generating what will be the next bit, the qubit that will dominate our life. And as opposed to this simple transistor that actually appeared in germanium, but is now silicon, that's sort of taken hold for almost a century now. We have a variety of choices as the unit of information, the successor for the qubit. And I'm going to talk about one particular implementation. It's an implementation in a material called 4H silicon carbide. Silicon carbide is a material that's already been used in manufacturing for high-power electronic devices and LEDs, and you can see that This is a photo from Cree, which is a company that manufactures those materials. You can get 6-inch wafers of silicon carbide, and moreover, you can get 6-inch wafers in what are called different polytypes. Different kinds of structures in silicon carbide, and those structures determine many things about their property, like their band gap, ultimately perhaps their mobility, but also has some influence for us. And the main character that I'm going to be talking about is this particular character. I'm showing you part of the 4H silicon carbide lattice. And what you see here, you see instead of silicon, which is blue, carbon, which is green, you see these golden balls. Those golden balls, we'll call them silicon vacancies. You're looking at them as if they are a thing, like an atom. They're actually an absence. They're the removal of silicon from the lattice. And because of the crystal structure, these are two inequivalent silicon vacancy sites. We give them names. We often call them V1 and V2, but there's also H and K. H means hexagonal and K means cubic. So this is the leading character that I'm going to talk about today. You're going to see this leading character in many manifestations. This is a picture of what it might look like if you could see into a 4H silicon carbide crystal and you were looking at the hero of this story. But in talking about this and in motivating our interest, and I'm going to show you a little bit about why we're interested in this particular candidate for a qubit. But for all of those qubits that I showed you, there are many important considerations in understanding whether it's suitable to begin with, whether it will continue to sort of progress in the race, and whether it may make it to the finish line, wherever that finish line is. And some of these are the idea of coherence. That is, if you have a quantum mechanical state like a spin, how long does that state remain with its polarization? So how coherent is it? For how long can you realize that it is a quantum mechanical state? Because that is the basis for any interaction that you carry on later. And then this, whatever the qubit is, whatever the hardware platform is, we have to consider the qubits. How do we entangle two qubits and across what distances? How do we prepare a state of qubits? So that's the initial state of information. And how do we read it out? And then we worry about integrability. How can we integrate these qubit candidates within networks as components? For example, what role do they serve? How do you implement a local memory so you can store that information for long times? How can you amplify the signal? How can you transmit that signal, cognizance of its coherence over long distances? Integrability with electronics or photonic or mechanical platforms. That is it going to be totally quantum mechanical in its operation, or will you need electronic processing? Will you need the assistance of photonics in your network? Will you need actually mechanical platforms? What other things do you need to consider? Different materials perhaps. And then the idea of scale-up, manufacturability, and that has a lot of meaning in many senses, and I'm not going to go into detail in it. And ultimately, the gorilla in the room is cost. To just introduce this briefly, and if you have more questions, Aaron will be happy to answer it. I'll be happy to answer it. I want to tell you a little bit. I just want to tease you with why we think the silicon vacancies in 4H silicon carbide are worth investing in at all. First of all, they have a spin state. This particular material has what's called spin 3/2. All that you have to understand is that there are discrete spin states, so that is a quantum mechanical unit of information. And this scan that I'm showing you, which is an optical representation that there are magnetic states. This scan says that when we hit the right energy difference between two different spin states, we see a response in the material, which is an optical response. So it's called optically detected magnetic resonance. And basically, to show you, it just means that we have spins in this material. We can get cognizance of those spins by reading it out optically, so that's very important. So it has that one part. It has that spin, that qubit, that local quantum reporter that's very sensitive to the atomic environment. Ancillary magnetic information, spin information, nuclear information, but equally, we also have an optical signature for this color center. So remember I told you there are two non-equivalent vacancies. We call one V1. V1 prime is an excited state of V1, and the other V2. And this photoluminescence spectrum at room temperature is a manifestation that they're alive and healthy and emitting light at their characteristic photon frequency. So this combination and this interrelationship is really important. We have a local quantum sensor, which is a spin, and we have a photon, and this stays local, but we have a photon reporter, and there are instances of its intensity and how we prepare states and the readout that are faithful reporters of the spin states, but these photons don't have to stay local. If we're very careful, we can send those photons over long distances through optical fibers so that we have the possibility of matching two of these qubits together over long distances, perhaps entangling them, and then going on with some kind of quantum information process. But that's the start of PROMISE. That's why we're interested in it. But there are so many things, obviously, that list that I pointed out to you. Is it coherent? Do I have ancillary parts of a network or that I can build into this material system? What about scale-up and manufacturability? But before we really consider any of those, and we are working on aspects of all those features that I listed to you, before we can go any further, and what I'm going to talk about today and what Aaron and Jonathan worked on was really answering a fundamental question. It's a fundamental question about how we begin to understand this material, these qubits, and where can we go. And what the fundamental question is, remember I showed you this cartoon of what the silicon vacancies look like. I showed you a very limited area. This is what we're looking at, but in point of fact, what it looks like is this. What it looks like here are silicon vacancies, but here is a local neighborhood separated by atomic lattices. And what you see here is a neighborhood of interesting characters with different kinds of behavior. So we have silicon vacancies. We have silicon, there's a carbon vacancy, which is this red, which is the lack of a carbon atom. So we have silicon-carbon divacancies. We have two vacancies that are correlated. We have interstitials. We have a whole variety of different defects. You might imagine they have different signatures. They may emit photon, they may not. They may have spin, they may not. But if you look at this, and you look at this neighborhood, you might imagine they're defects. if you've done anything with materials and perfect materials, generally you think that defects are something that you want to remove from your material, so you do processes like annealing. You give the atoms in your material enough energy so they can move around, go to a minimum energy, and voila, the defects are removed. So here's the possibility of recombination. So the big question we need to answer first is, how can you form the desired color centers, in this case the silicon vacancy, in exactly the right position, with exactly the right properties, and I'll expand a little bit right properties, without creating a surrounding atomic scale community of undesirable defects. So just to give you a cartoon of right properties, right positions, I've just drawn a cartoon of a number of spins that you might begin in an array in a material. So these are, read for these spins, the spin of a silicon vacancy, nicely aligned in array, every spin in its place, nothing around them to interfere. All we have to worry about is how to connect those spins together. But in point of fact, this is what the neighborhood looks like. And the right properties, if they're surrounded by other defects that you didn't intend to fabricate, then those are sources of decoherence. Not only are they sources of decoherence, they're possible sources of destruction. Because if you give a little energy to the material, maybe a carbon interstitial will interact with a silicon vacancy and create something completely different. So this is the big question, and this is what everybody worries about. And this bill everything is anomaly, because we're working with quantities that give off light, and they're atomic in size, or they can be molecular in size. It's almost easier to take a single atom and then maybe hold it with a laser trap and then play around with it than to create a defect in a material that has its own properties surrounding it and expect to be able to create what you want, where you want, in the environment that you want. So what's the answer to this big question? What do we need in order to address this fundamental problem? And so I would argue is that what we need is a technique for the creation of these color centers that provides real-time feedback, so that as we create the defects in an environment, we can change the way that the energies we use to create it, the spatial profile of the instruments we use to create it, and get real-time feedback so we can adapt what we do and learn from the process. Not artificial intelligence, real intelligence by making something in situ. And what do I mean by that in terms of formation? So I've told you how we form them, but you can guess. I had a model of an atom, but you can guess. You can guess if I'm creating vacancies, if I'm removing silicon from a silicon carbide lattice, what I must be doing is actually doing damage to the material. I must be interjecting kinetic energy into the material. I must have some kind of kinetic energy so that I can break bonds between two atoms. And once I break the bonds, it's easier for me to form vacancies and interstitials and a whole variety of defects. So the traditional way of forming color centers, whether it's in diamond, whether it's in silicon, whether it's in silicon carbide, whatever the community uses is, I'm going to take a hammer and I'm going to smash it into the material and hope, as a result of that process, that I've broken enough bonds so that I create the qubits, the color centers that I want. So, for example, ion implantation. These are conditions we often use. We use carbon ions, accelerated at 70 keV, And the dose matters too, because the number of ions you use may dictate the number of color centers that you form. Also, electron beams, neutron beams, focused ion beams, anything that actually you can direct against the material, that basically idea is to exchange kinetic energy and break bonds. What's the problem? The problem is, yes, we want to damage, but the problem is you're damaging. And also the problem, even with all the beautiful modeling and the knowledge that we have about charged beams that have been generated for 70 years or more, it's still a stochastic process. You still don't know exactly where that ion is going to go and stop. You know it's going to give energy to the lattice. But even if it stops and transfers energy to the lattice, you don't know for sure you're creating the defect you want. All you can do is large-scale characterization ex situ, draw inferences, try to model it, and try to figure out what's happening. And this is an inefficient optimization process, because what you do is send out your wafer to somebody who does ion implantation. Or maybe you use a TEM and do electron irradiation. But most often you send it to someone who actually provides that service. And when you send it to someone, even if they get it back to you within 3 days, what you have to do is you have to specify the energy, you have to specify the dose, and you might have to send 3 different wafers, 3 different samples to span that range of conditions. And then, you don't have direct handle over the conditions that create the defects, and then you get your sample back, and you do various kinds of post-processing, you look for your color centers, and then you infer. But you don't really know, when you see what you see, what are the unique conditions that produced the good color center performance, if they are good, or the full color center performance. So that's how this kind of fabrication is usually done. What have Aaron and Jonathan instead? They've devised a new process. This technique, just to show you some images, is using a laser, not a charge beam, using a laser to focus, to directly, the term we use is write, because when you use the laser and you scan it over some surface, you're actually writing or creating the defects that you want. But we're using a specialized stylus. That's a laser, and it's a particular kind of laser. But we're also using a particular kind of tablet. The tablet is shown here as a cartoon, but it's shown here in the scanning electron micrograph. And these are a series of arrays of photonic crystal cavities that are written into silicon carbide. And we choose this tablet because as we write, we've designed this tablet to, once you actually, the tablet is sort of like a trainer, one of these trainer programs, these trainer apps, when you're starting to learn anything, reading, drawing, it gives you almost instantaneous feedback that, yes, you're doing the right thing. Yes, you've created the color center that you want, and you've created it within the spatial location that you intended to. So how does this work? And just before I go on how does it work, I want to tell you that it does work. So here is an example of a photoluminescent spectrum. And so what you see here is this orange scan is the spectrum that we got because the cavities are. Didn't put any color centers deliberately into the tablet. There might have been residual silicon vacancies in the tablet, but we think not so much because we see this background. We see a little bit of resonance. This resonance It's called cavity. This resonance is actually saying that the tablet is doing what it's supposed to do, because the tablet is a delicate instrument. I'll show you another slide, that actually once you get any photons within the same wavelength or frequency of that the tablet is designed to respond to, you actually see a strong signal coming out from the background. But what is here, this is a single shot laser pulse formation, and I'll give you a little bit more information later. It means that the stylus is not smooth writing. The stylus sends out photons in pulses that the spectrum looks dramatically different. Not only do we see these cavity modes here and here, but we see a peak emerging at a wavelength that says, I'm V1. I'm actually evidence that whatever you did between stylus and tablet, you've created some silicon vacancies or color centers. So let's take a further look. Let's look at the tablet. And this, again, is something that we couldn't do without CNS. Here's a tablet and a different view of the tablet. So what you're looking at, this is a scanning electron micrograph. What you're seeing is the bottom of the substrate, which is silicon carbide. You're seeing the nanobridge, but the nanobridge looks like it's right on the bottom. It's actually suspended above the bottom by about 600 angstrom or so. So this bridge, we call it a nanobridge, is not in direct contact with the bottom. And that's important because we need to optically isolate this silicon carbide bridge. And what you're seeing here is, just take a look at this bridge, which is pretty homely. I say that this is a photonic crystal cavity. We've designed this. It's basically a bunch of holes punched into 4H silicon carbide. So this dimension, this width is about 200 nanometers. This is a side view. It extends about 200 nanometers. And there's maybe less than 100 nanometers or so from hole to hole. And the holes are not equally spaced. There's a reason for that. And then they are not, you can almost see that there are slight changes in dimension. So very small features. This is a 1 micron bar. And what you see, so imagine this. What is the purpose of this tablet? So imagine that we launch light through this nanobridge. And the nanobridge, think of a wind instrument. Think of a recorder. A soprano recorder, if any of you play wind instruments, soprano recorder, an alto, a tenor. You know that instruments give you different resonance responses. It depends on their size, even string instruments. So there's something about the size and the composition of an instrument that together, when you have energy coupled to that instrument, and in a wind instrument you blow into it, so it is acoustic energy. If the instrument is finely made, you see a beautiful resonance. You see a clear response. And that's exactly what we're looking for here. And how do we see that clear response? So imagine light going through this, this nanobridge. What it sees is, because there are holes, it's silicon carbide hole, there is a modulation of the index of refraction. Therefore, there's a modulation in the speed of the light. Ultimately, what happens is that there's a standing wave pattern that's set up at the right frequency. And this, what you see here, are representations of that standing wave pattern. And we've actually achieved these, we didn't just draw these in, by using a design tool where we do electromagnetic simulation of what we expect. So what you see here is actually that standing wave. You're seeing the maxima of electromagnetic fields. They are, as standing waves, they are long-term solutions for the resonances of light at a particular frequency that we use to design this. And where you see the red to yellow to white, the white is the maximum of the intensity. So imagine we have a very high density electromagnetic field, top-down view, side view. And the quality of our instrument, the way that it responds to the right energy is given by a factor we call it Q. It's the fine-tuned resonance. It's how well it responds to exactly the right frequency, and how well it responds is sort of one measure of it is how narrow is this peak wavelength. So this cavity quality factor is a factor of 5,300. We get that by looking at the wavelength over the half width. So to tell you, the tablet, we've derived and designed the tablet so it responds, in this case, to the one frequency. So this is a tablet that's limited, but it's good for what we want. It tells us if there is a V1, if there's a silicon vacancy there, it will likely show up clearly from the noise, as you saw in the last spectrum that I showed. So that's the tablet. I want to show you another picture of the tablet because this is important in our understanding sort of how we begin to learn about the environment of defects. So here is the side view of the photonic crystal cavity. I've tried to impose on it the views of the electromagnetic field within that cavity, and I'm drawing tune. So imagine we created a number of defects. Okay, we didn't just create the silicon vacancy, which is blue. We also created carbon vacancies and silicon-carbon vacancies. And because it's crowded there and I ran out of symbols, I'm just going to show those three. But imagine it's a really messy environment that somehow I created a defect environment. And I created a defect environment in a volume that is about 100 nanometers by 100 nanometers by 100 nanometers. So it's a little cube, roughly speaking, about 100 nanometers cube. It's a pretty volume, but these are atomic scales, so I could have lots and lots of defects. But imagine what I'm doing. Why is this a nanoscope? Because insofar as these color centers, first of all, have the right frequency that makes the tablet resonate and really send out light efficiently, and insofar as they are in the same spatial location as the maximum of the field, I'm going to get the greatest signal about it, of them. So I get the best information from color centers, defects. Again, think about that diagram that I showed you with silicon carbide with, just atoms ripped out, interstitials there, and it's just a messy neighborhood. But that messy neighborhood, I can begin to parse out what's going on here if I have the right feedback in terms of where is it, that lets me know a little bit more. Where is it? And what frequency is it emitting? So this cavity, our tablet, also gives us sensitive optical information about the ensemble, maybe not a single defect, the ensemble of defects confined within this volume, and both the spatial location and the frequency, although we have to do a little bit of inference. So now let's look at the stylus. The stylus here is a laser beam. It's focused by an objective, let's say to 4H silicon carbide. And our stylus is a nitrogen laser. It has a wavelength of 337 or so nanometers. It's UV. It's in the range of UV, not deep UV, but the range that's important is Here's another representation of 4H silicon carbide. It's a different view of 4H silicon carbide. It's not the atoms, but it's the view of silicon carbide, 4H silicon carbide, as a semiconductor. It's not a faithful replication of the band structure of 4H silicon carbide, but quite simply, what we're looking at is there is a valence band that is largely full of electrons. There's a conduction band that has lots of energy states for electrons to go in. The conduction band edge and the valence band edge is separated by the band gap of 4H silicon carbide. And that energy is 3.26 electron volts, or that corresponds to 369 nanometers. And the big deal here, the big deal for the process and the big deal for the innovation of this project, of this particular project, is that the wavelength, or the energy of each photon from the laser we're using, is larger than the valence band to conduction band. It's larger than the band gap. And as you'll see when I try and explain what we might expect by using this stylus, you'll see that that's an important point. And Mac had a question earlier, where are these impurities? Whether it's doping or not? The point is that once we add we change the structure, even locally, of the material, we imagine, and I have another diagram if you want to see, but we imagine that defects, because they're the unusual things that we've done to the material, they now occupy states within the band gap. And that is an important point. An important point going on, because if the energy state is here, mid-band gap, and this band gap is large, what you might think happens is it buys you a little bit of stability with respect to electrons, the electron environment, the electrons that might came from the valence band or conduction band. So having an isolated energy state here buys you a little bit of isolation, electrical isolation from the surrounding electrons. That's looking at it. And in case, for those of you who know semiconductors and know doping, if we have impurities that we want to use to dope a material to make it look N-type with a lot of electrons or P-type with a lot of holes, we put those energy levels close to the conduction band or close to the valence band. So these defects that we want to remain stable, we hope they have energy levels basically mid-band gap. So what do we think is going to happen? And what I'm going to tell you is what we think may be going on, and that's based on hundreds and hundreds of studies that took place probably in the 1970s, 80s, 90s that looked at laser damage in materials like diamond, SiO2. They were called so-called, they're essentially high band gap materials, although you might not think, you might not think of them as semiconductors. So here, and those studies actually, when they talked about damage, they really meant damage. They meant micro-machining the structure. So here's the process. The laser, to electrons in the valence band. And depending on the fluence or the density of photons that you have that are above band gaps, what I'm showing you is a notional picture of what happens. The laser lifts off a huge number of electrons from the valence band, promotes it high up into the conduction band. Now you have a lot of electrons, you have a high density electrons. How high a density? Maybe 10 to the 20th per cubic centimeter, but the valence band doesn't care, because essentially the valence band is almost an infinite source of electrons. So what you do is you create a high density of electrons and holes. What you hope is, in a process, that these electrons, so imagine a bunch of electrons out here, They have energies way high in the conduction band. They have such high energies that some of those electrons can go back and interact with electrons in the valence band and knock further electrons out. So this is a sort of an avalanche effect. Avalanche meaning I deliberately create excited electrons. Those excited electrons in turn have enough energy to scatter against electrons and sort of lift them from the valence band. The term we use is ion. Sort of feed forward. One excited electron doesn't just end there. It doesn't just de-excite, go back to the valence band, but it continues this process of cascading, exciting electrons, and it's called an avalanche effect, which is nonlinear. And then if the density of electrons here is high enough, because first you had this 4H silicon carbide, now you've changed the material by creating a huge density of electrons. That huge density of electrons in turn absorbs the laser light more readily. So this is feed forward. This is, first you absorb. Absorbing means taking the energy of the laser and transferring the structure of the 4H silicon carbide, but now once you create the electrons, and some researchers call it a plasma, you just feed forward and increase the absorption further. It becomes highly nonlinear, and ultimately it's these electrons that have enough energy to break bonds, create defects. Those are the color centers. So the process of creating these color centers in a way is not so different from what I described here. Here, where you have electrons with kinetic energy going in and breaking bonds. But what is different is I'm utilizing the properties of the material itself. So it's like self-destruction. I'm using those electrons. The laser gives you the energy, the electrons are in turn. That has actually a lot of consequences and a lot of insights that we may be able to use. And I just want to say, in describing our stylus, I just want to say that we, in this context, we were the first ones to try using a UV laser to excite above band gap. All previous laser writing techniques to create color centers, whether in diamond or silicon carbide, were below band gap wavelengths, not UV, something like 780 nanometers, which meant, and they were femtosecond pulses, ours are 4 nanosecond pulses, which meant this picture, which I show one arrow creating the excitation of electrons, this picture would be multiphoton. So it would be a series of arrows building up to try, because ultimately you have to free the electrons here, get them up here, get them really excited. They have the energy to actually feed forward the process. And so we think, actually, I've shown you evidence that it works, but we think perhaps this is a much more efficient way of doing it in terms of the energy needed to create this cascade of electrons. Now, having given you this very nice notional description, I want to tell you that we don't actually know that this is the mechanism, and that's part of the exploration that we have to continue to do. But I will say this, I'll show you more of Aaron and Jonathan's data. It works. I already showed you a PL scan that shows that it works. Here is another example. Here are arrays of photonic crystal cavities where we did not deliberately add color centers. There may be residual natural defects. And here's an evidence, here's this positional map where Aaron actually changed the position. So the question is, is the focus good enough? Can you actually read the portions on your tablet so that you can actually deliberately change the position and know what you're doing? And the answer is yes, because if you're very far off from the sweet spot, and the sweet spot, remember, the sweet spot is where I showed you those electromagnetic fields, which are sort of going from red to bright white. In the middle of these cavities, if I'm very far off, imagine this is sort of the sweet spot. If I'm very far off, I just get the background. If I go a little bit closer to the sweet spot, I see a background. The background is higher in intensity, but I begin to see structure that I'm relating to the modes, the natural frequency response of my tablet. And then if I go still, I see the background increase, but I also see the cavity response increase. So it works. And this is an example of this sort of real-time positive feedback because we happen to know we have a tablet that says right here. But what if, we have different materials, we were exploring another structure? This is an indication. Just to show you that not only can you get that real-time feedback, if you have lots of arrays of cavities and you have the time, you can actually just play around with writing. So to some extent, it may still be a statistical process, but it's a statistical process with feedback that's under your control. So you use your laser, you use a certain fluence, and I'm going to show you more about the fluence, and you write 20, 30, 50 cavities. And what I'm showing you here is important because in our other experiments using the traditional techniques, where we send off our ion implantation, we get it back, and we make the measurements, we often see V1. We almost never see V2. And there may be many reasons for this. A lot of this is still unknown, whether the energies of formation or energies of recombination are very different. But this is an example of an isolated V2 that is a K-site. And this is the corresponding, I showed you this before, this is the corresponding optical signature, that self-same defect. And the last topic that I want to show you that actually, this is not Aaron's favorite part, I think. I'm not showing Aaron's favorite part because you should ask him. But this is my favorite part that Aaron did, which is he decided to take a structure, like he found he had a V2 or he found he had a V1, and we see more V1s. And then he decided to measure the lifetime of these defects. So what it does is you have a defect, right? It has ground state, excited state. You excite it. Once you know you have the defect, you've written it, you excite an electron from ground state to excited state, and I think some of you know this, it has a natural lifetime, or you can change that lifetime. But it has a lifetime before decaying with a photon. And we're going to make some inferences about what that lifetime means. So Aaron's genius was that he looked at lifetimes over different stylus energies, that is, different laser fluences, and sometimes for the same fluence, but 1 shot, 2 shots more. And he tried to see, is there a relationship between the energy I use to form these silicon vacancies, and I can tell I have them because I see them coming out clearly in the tablet. Is there a relationship between the energy I use and the lifetime of the color centers I create? And just to show you a little bit. So these are, this is using 0.475 microjoules per pulse. So the fluence, or the number of photons per pulse, in both cases are the same. In one case, there's a single pulse, which is this, And the other case, there are actually 2 pulses. So what you see here, so number 1, I'm going to show you a table that shows actually it's an amazing correlation that makes us want to infer something that's quite important. But the other thing is that often he sees something that looks like a single exponential decay, and then very often he sees 2 exponential decays. That is a short decay, a long decay. This long decay for the single pulse is suggests a longer lifetime, but then there's initial short. So it's not a single exponential. So just for example, this is one of his traces for data for a certain fluence, but let me show you something altogether, and it helps us answer the question, is there an optimal laser fluence to the creation of these color centers? This is not something we could do with the ordinary technique, where we send out 5 wafers and we have them implanted at different energies and different doses, and then we get them back. And we don't have it under our control we can only infer because we didn't do the writing ourselves. So I'm going to show you this graph, which I still think is amazing, and let me walk you through it a little bit. On the x-axis is plotted the fluence in microjoules per pulse. So basically, from left to right, you're changing, let's say, the number of photons per unit area per pulse here. Lifetimes of the excited state lifetimes of the color centers you create are plotted on the y-axis. And then for any given fluence, you have single pulse or multiple pulse, which may be 2 pulses, and then there's more than one data point just to show you the variance in the experimental error. So what you see is, remember, we have a long lifetime and a short lifetime in general, so bi-exponential or multi-exponential. And interesting, if we take a look at the long lifetimes, single pulse, multiple pulse, 1 fluence. Single pulse, multiple pulse, a slightly higher fluence. Single pulse, multiple pulse, higher fluence yet, 6 microjoules. The long part, the one that has that actually may be an indication of the real lifetime. You see the TL, tau L, changes as we change the conditions of writing the color center. Whereas if we look at the short pulse, that first rapid decline, what you see is that the short pulses all cluster around here. They're all associated with a sort of a very short lifetime, and they're not sensitive to the conditions of writing the structure. So what is our inference, and why do I find this so exciting? Here's the assumptions, and you challenge the assumptions. The lifetime of the color center we create, the optical lifetime has to have some relationship to the local atomic environment. You can imagine if it's an optical lifetime, and we don't have cavity amplification, that just imagine, and there may be, there's some mistakes in my reasoning. What would cut the optical lifetime? Well, if there are traps nearby, if there are other defects or imperfections that would, I promote an electron to an excited state, but instead of waiting its full lifetime and emitting a photon, it gets caught by a trap. The electron gets caught by a trap. It never radiatively decays, number 1. So here's the assumption. Could we infer that maybe at the very highest energies, the higher energies, higher fluence, or using multiple pulses instead of single pulse, maybe we have that extra energy. That extra energy coupled into the material is creating more ancillary defects. I'll call them collateral defects, defects that we don't necessarily want. Maybe those collateral defects in the surrounding area are what causes decoherence. Maybe what we want is the minimum energy that we need to create the defect, low enough so we can create the defect, but not so high that we're creating an ancillary, a neighborhood of other defects. So this is the reasoning and why it's so exciting to me, but in general, this is something we could never do with the other technique, which is to do these kinds of experiments, begin to think about something we can control, which is the energy we place in to create the defects and get the feedback to make the measurements that we need to make that inference. So, and just in conclusion, I've told you about this is the big deal, a technique for color center creation that provides real-time feedback. And most of all, real-time feedback, why is that important? Because it gives us an opportunity to learn and to adapt. I talked about the new stylus, which is an above bandgap laser. It's not actually been used before for this application. It's above bandgap, that's number one. It's slow compared to the femtosecond lasers that have been tried before. A different kind of tablet, writing into, let's say, a smart tablet, which are photonic crystal cavities that amplifies, that gives us feedback, but also gives us an amplified feedback. I've shown you the formation of H-site and K-site silicon vacancies. I showed you a spin signature that says that indeed these defects also have a spin life. Our ability to begin to understand optimal formation energies, and just wind up by saying we're just at the edge of the frontier. Honestly, I gave you what it may or may not be a convincing story by what we think the laser is doing, but what actually is the mechanism of the silicon vacancy formation? What is the dependence on material, purity, on laser wavelength, on material at all? Does this technique work with other materials? Something I didn't talk about, which you should talk to Aaron, because this is also important. He's done experiments that show that the laser can be used actually to do annealing, in the sense that it can remove a background of sort of a background that appears in the photoluminescence that may be related to states that exist on the surface, and that would be major. And again, can we apply this technique to other materials in color centers? Ultimately, can we create deterministic single photon cavities? And with that, besides Aaron and Jonathan, who were the principal people who pushed forward this paper, Maddie and Matt helped in writing the paper. Lizette Amberly Chan are working on the silicon carbide platforms right now. And I'm not showing all the former students who've worked on this, but I have to point out David Bracker and Alex Zhang, who graduated a few years ago, but in particular, David did all the initial work working with 4H silicon carbide, deciding how to make these photonic crystal cavities. And he and Alex both did some really critical experiments in tuning the cavity. So thanks for your time, and thanks for being here.
So before you ask questions, I have to run to a budget meeting. So I want to offer you sure that you have one of the seminar series coffee.
Thank you. Thanks very much.
And again, thank you for coming, and hopefully I'll get some money out of this. I'll see you guys.
In the budget meeting. I wish you luck.
Okay, if you have a question, raise your hand.
And I have to say, I have a meeting too. I will stay to answer questions, but putting Aaron on the spot. Aaron can answer every question you ask about this. Mac.
Okay, well, as I understand it, you create the silicon vacancies with the laser, yeah? Yes. And it sounds like you essentially ring the bell with the same silicon, or with the same laser. In other words, you activate and you watch you create the resonance in the same, essentially in the same event?
Not quite. So we use a UV laser, above bandgap laser, to create the defects. The photoluminescence is done, we excite the photoluminescence using a different wavelength laser, if that's what you mean.
Yeah. It sounded like it was occurring in the same event.
Yeah, no.
So those are static vacancies that are going to stay there until they're annealed out or something happens.
I will answer that. I think that they are static over the time frames that we've looked. I can't assure that, so there is probably a hopping constant that's very long. If we look, and Aaron might have more knowledge about this, if we look at the same cavity over several weeks, actually we do have experience on this. The cavity will oxidize, the modes will shift, but we don't see actually, until we do like a thermal anneal or we do something more deliberate, we don't see a change in the defects. Aaron?
Yeah, it's very long-lived. We can go back to the same site and the defects are still there many months later.
Thanks.
So by the way, can you tell us how do you floating the silicon carbide beam on silicon carbide substrate? What's the process you used?
So that's the topic of another talk that maybe someone, Aaron, Jonathan, maybe Amberly is beginning to work on it. It's a process that we developed called photoelectrochemical etching. And it's a process that can be bandgap selective or dopant selective.
That's great. Maybe next semester we can arrange another talks. Okay, great. Any other questions?
Thank you. Thank you.